Double bonds. How do you know when to be drawing double bonds in your compound? First, when you draw your skeletal structure and you have your central atom and you have your outer elements, always draw them as single bonds to each other. Never draw them as double bonds from the beginning. So draw single bonds first, bonding all the outer elements to the central atom first. And then, because you know how many valence electrons total you have in your compound, give all the outer elements 8 electrons first. If the outer elements do not have 8 electrons and you've used up all of your valence electrons, that's when you should start thinking about doing a double bond. Or you've given all of the outer elements 8 electrons and the central atom does not have 8 electrons. Again, you need to be thinking about double bonds. You have to use up all of your electrons and you must not invent new electrons. You should always be aware of how many electrons you started with, how many valence electrons, how many did you use for bonding, you should be minusing that off, and how many are left to use to make everybody happy with 8 electrons. Carbon dioxide, let's draw carbon dioxide. Now I've told you it would be a double bond, but when you're first drawing compounds you will not know if there is a double bond or a triple bond. Determine the number of valence electrons as we've been talking about by looking at your periodic table, looking at your group numbers, and multiplying them by how many exist in your compound. I will have a total of 16 valence electrons in carbon dioxide to be using. Draw your central atom surrounded by the outer atoms. Again, the rule is if there's more than one of the same, they're definitely on the outer one. You're going to use I use a straight line to represent the bonding between the central atom and this. That means I've used 4 electrons. When I minus that off from here, I have a total of 12 electrons left to make everybody happy. You need to be doing that on the outer elements first. So I'm going to use these 12 electrons and put them around each of the oxygens. When I use these 2, 4, 6, 8, 10, 12, I've used up all of the remaining electrons. However, when I go back in to see if everybody has 16 electrons, I notice that carbon only has 4. That's when you begin to say, okay, I've got to shift some of my electrons around here. So I'm going to take these 2 electrons and bring them up over here. I could have taken those or those. It doesn't matter. The symbolic thing is I'm taking 2 electrons from oxygen and I'm going to shift them over here to the double bond to carbon. Alright, let's see what that looks like cleaned up a bit. Here it is. Now when I do that, this oxygen will still have the use of 8 electrons. But carbon now has 2, 4, 6 electrons. So it's getting better. In chemistry, as there is in biology, there is symmetry in our compounds. So this one has a double bond on this side. I'm going to make a double bond on this other side. So I'm going to take 2 electrons from this oxygen and again do what I did up there and bring them over. I guess I did that. They took these top ones and brought them down here to carbon. Carbon now has the use of 8 electrons. Each oxygen, when you count them up, has the use of 8 electrons. Now, it's fine to have the drawing appear like this because what you're saying is there's 2 double bonds that exist in this compound and then there's 2 sets of lone pairs of electrons that sit on each oxygen. 2 sets of lone pairs of electrons that sit on oxygen. Or you can make it nice and pretty like this drawing does. But they really are saying the same thing. 2 double bonds, 2 sets of lone pairs on oxygen. Both of those would be acceptable. Let's take a look at what is wrong with these Lewis structures. Let's see what are the rules they are not following. Let's take a look at some of these of why these would not work. Let's take a look at C down here. Look at how many electrons are around carbon. There's 2, 4, 6, 8, 10. Remember, you can only use, they only need 8 electrons. But if you did count the total valence electrons used in here, I'm sure it would exceed the 16 that you were allowed to use. 2, 4, 6, 8, 10, 12, 14, 16. So they used 18 valence electrons, which is a common error by students. You can't do that. You're only allowed to use 16. Take a look at this one. Carbon has too many electrons, 2, 4, 6, 8, 10 again. That one's not correct. This one we just drew and we said was correct. Alright, take a look at this one. Looks really close to A. However, again, take a look at carbon. It has 2, 4, 6, 8, 10, 12 electrons. 14, 16, 18, 20. This one even has a couple things. Too many valences and too many electrons on the central atom. Now this one did use the 16 electrons, and each of these do have 8. However, the most electronegative atom is in the center of each of these compounds. I don't expect you to know what element would be in the center, and that's why I would underline it in the actual formula of the compound so that you would at least know who would be in the middle. Nitrate with a charge. Let's take a look at that. Here it is, counting the valence electrons. Remember the charges, you need to add whatever charge that is to the total number of valence electrons. So adding that, I'll get 24 electrons. I immediately bond them to the outer elements of oxygen, so I've used 6 electrons, so 24 minus 6 means I have 18 to make everybody happy. I'm going to use those remaining 18s on the outer atoms like I said. Remember, start with single bonds and then distribute the rest on the outer elements. And so I did that here. I've used up, if you count all of these, I've used up the rest of the 18, and this whole compound contains 24 electrons. Now each oxygen is okay, however the nitrogen in the middle is lacking 8 electrons. So I'm going to take one of these pair of electrons, again on an oxygen, and I'm going to bring it up to make a double bond. When I make that double bond, it will give nitrogen 8 electrons, and it still has this oxygen have 8 electrons. However, the reason why this is called a resonance is I could have taken a pair of electrons from here, or I could have taken one from this oxygen, or I could have taken one from that oxygen. So there is no rhyme or reason which oxygen I chose from first. And here is a drawing of what this would look like. This one has made the double bond with this oxygen. But resonance structures is just that. This double bond over here could have been drawn over to this side or to that side. And so actually there are 3, and they're all correct, and they should be drawn, of this nitrate ion, showing the double bond being switched between the different oxygens. And actually, when a compound has a charge, you should be drawing square brackets around it and indicate its charge on the outside, because it has that shape based on the fact that it does have that charge. If it didn't have this charge, it would have a different structure. So this is a resonance structure showing that all 3 of those exist. This is So3 Sulfur Trioxide. Again, calculating how many electrons there exist. Draw the skeletal structure, bond them. So I've used 6 electrons. Minus that off, I'll have 18 to use and distribute around the oxygens. And so I'm going to do that over here. And I've used up all 24 electrons, and all oxygens are happy again. However, sulfur does not have the use of 8 electrons. Again, I can take a pair of electrons from this oxygen and bring it down to make a double bond. Or maybe I could take a pair of this and bring this one down, or this and bring this one up. So this is another one that is a resonance structure. And on this particular one, the double bond came from over here. But this this compound can be drawn with a double bond here and there. So all 3 of those should be drawn on the exam. And those are resonance structures. So this gives you an idea of how to discover when double bonds and resonance structures do exist.